On slide 40, we turn to DSEM analysis. So that is two-level analysis where we bring time into the model. I'm going to start with DSEM for a single outcome. And I'll call that step 3 in our 5-step analysis of the data. So we're considering two-level modeling using DSEM, a univariate analysis of positive affect. I'm going to take a look at 3 different ways to describe the model, and you may favor one over the other. First is a model diagram, second is statistical formulas, and the third is Mplus input. Over time, I think one changes, and Tiamer and I were talking about that the other day, and we're thinking of the models more and more in terms of the input itself. There are, of course, alternative ways to draw the model diagrams, and you will see different alternatives in the literature. There's always a balance between drawing them statistically correct and simple enough to capture it visually in an understandable way. Here's how I favor drawing it right now. So we have the within level variation over time, where we show a lag 1 relationship, PA at time point t regressed on PA at time point t minus 1. And when we have a between level part of the model, which is variation across individuals. So you have within and between. And the observed variable is decomposed into a within and between part in this way. The between part is a random intercept varying over persons, which is also referred to as a latent trait. So this model diagram is drawn in line with cross-lag panel modeling with random intercept, RICLPM. See it, for instance, in the Mulder and Hammacher paper from 2021. That's on our website under RICLPM. So we break out the between level random intercept here, influencing both time points, and show it explicitly influencing those variables. So let's step back for a second and ask ourselves, what's different in this drawing from the regular two-level drawings that I showed in previous slides? Well, first of all, we have 2 time points drawn, which just exemplify a sequence of time points. It's just a slice of time. We draw the adjacent time points. If you want to, you could put ... here on the right and on the left, ... meaning it continues backwards and forward. And also, a second point is that compared to the regular multi-level modeling that we talked about, two-level modeling, is that we draw the residual relationship explicitly in the figure here, exemplified by the within part of the model. Now, there's several conventions then in drawing this that are sort of implicit and become second nature after a while. First of all, what we mentioned is that we only draw 2 adjacent time points, t and t minus 1. And the second is that we draw the observed variables outside the within and between boxes, because they're neither within only or between only variables. And the second or third thing rather, the regression coefficient for the observed PI variable regressed on the latent between PI, on the latent within PI, are all fixed at 1. So these arrows all have coefficient 1. And also the residuals are 0 for the observed variables, which means that the observed variable is the sum of the 2 latent variables, reflecting the within-between decomposition of the observed variable. So any variable here is influenced by 2 sources, the between plus the within, with weights 1. Between plus within, very simple. Just a decomposition, no residual up here on the observed variables. The latent within level PA variables have residuals, and we've drawn that here. So there is where the residual ends up. Now, note also the last convention here, that the full within part of the model is shown only for the later time point, for this time point. We have a residual also for the earlier time point, but we don't draw that. So everything in the model, for instance, or later on a random variance, is drawn for the last time point here, but it exists throughout the series, going backwards and going forward. It's just a convention. Now, if you look at that from the point of view of formulas, relating to where we ended up just before we turned to DSEM, where we ended up in our discussion about regular two-level modeling and what was missing there, we talked about the observed variable being expressed in terms of a random intercept, alpha, which is labeled PA in the between box in the diagram, and a latent variable centered PA IT minus 1. So we have this latent variable centering here once again, and that is the latent variable centering that is the key to the analysis, avoiding the so-called Nichols bias, which is discussed in the original paper of TMR in 2018, Asparahov, Hammacher, Muten. If you want to read more about centering choices, you can read the Hammacher-Grossman 2015 paper in Frontiers of Psychology discussing centering in general. But latent variable centering is the key. And just like we did in previous slides, we can move this alpha over to the left-hand side here and define a latent variable which is the difference of the observed minus the latent between, and we call that within. So then we have the within part of the variable is beta times the within part of the variable at the previous time point plus a residual, which is exactly what we have up here. This is PA within for time point t, regressed on PA within time point t minus 1 with the regression coefficient beta and residual epsilon. Now we're going to stay with the fundamental issues here a little bit longer. The third way of looking at this model is through the Mplus input, which is very simple. In the model command, you have the within and between parts of the model, because it's two-level, and you say on within, PA on PA ampersand 1, so a lag 1 variable. So this regressed on that, and it's a lag 1. You can have lag 2 as well here, of course, but this is the simple model. And then you have variation in PA also on between. You don't have to mention the residual here in the regression. That's a default. That's included already by default. Now the within level slope, this one that we call beta in the previous slide, that's the autoregressive feature, as well as the residual variance, can be random, that is individual specific, varying across people. And that would then add latent variables to the between level. This is what varies across people. And note that Mplus is much more general than what it looks like here. It actually allows a full structural equation model to be specified on each of these two levels, within and between. So for instance, you can have a mediation model on within and on between. You can have a factor analysis on within and on between. You can have a full structural equation model on both levels. But we're going to keep it simple, fairly simple throughout most of this talk. Now, we should recognize that there are alternative ways to draw these DSEM model diagrams, and in fact, I draw them differently in the Mplus User's Guide. You've probably seen this drawing here in a simple case. The random, we have a regression of PA at one time point on the previous time point, and we mark random effects like a random intercept here, regression, y equals a plus b times x. You have the random intercept, or the intercepts rather being random. marked as a filled circle on within, which then becomes an open circle, a continuous latent variable on between. That's very simple visually, but it's not statistically correct because we never regress the observed variable at one time point on the previous time point. It's a within part of it that we regress, and also we do a centering here. But it gives you the general idea, but not very precisely stated. Now, Ellen Hammacher has a different way of doing it, which is statistically precise. She emphasizes decomposition into within and between level variation. So first she considers a decomposition. What I talked about before, the observed variable is a sum of the between part and the within part. Here with coefficient 1, again, just simple sum of the two. Whereas where the within part has subscript t, but the between part does not. It doesn't change over time. And then for the within part, she has a model, the same model, regression, on within with a residual, drawn for the last time point, and then between part like that. So that's a nice way of drawing it as well. Now, the style that I've chosen for this web talk, which I like, is compared to the user's guide style, there is no filled circle for the random intercept. And instead made clear that the regression is for the within variables, implying latent variable centering. So no filled circle. Instead, we have the between part of the model drawn as influencing the observed variables. So that implies, since it has unit loadings or unit coefficients here, same coefficient 1 across time, it implies it is a random intercept. And we see it very clearly then in the drawing, and we don't have to work with any filled circles for that. We pull that out separately. Now compared to the Hammacher style, there's no decomposition drawn, so it's simpler visually from that point of view. And the role of the between PA as a random intercept is instead emphasized. So in the Hammacher drawings, you don't have this connection. And there are no W or B superscripts for the variables, but instead the variable names match those of the input. Now, it's interesting that this style of drawing it is actually done in Hammacher and Mulder's work when they talk about RICLPM, but Hammacher decided not to do it for DSEM. So there are pros and cons of these different diagram styles, but just want you to be aware of them. Going to slide 48 then. What defines a DSEM run in Mplus? And I'm often using the term time series analysis. DSEM to me is multi-level or two-level time series analysis, or cross-classified time series analysis, as opposed to regular two-level analysis. Well, the key thing is this lagged option, triggering DSEM by allowing the ampersand, the lagged variable. So if you go back one slide here, it is this relationship can only be written out in the model command if in the variable command you have specified lagged. So it's the feature of talking about several time points in the model and several lag time points in the model. Then you can access the general modeling of lagged variables, lag 1, lag 2, etc. We talked about the T-interval option earlier on, and that can only be used if you have specified the lagged option in the variable command. Now T-interval is not necessary for lagged, but not using it would assume that time is simply 1, 2, 3. which is maybe not what you want for your data. Now, before we get into the analysis with this model for the data, we need to talk about stationarity a little bit. Now, stationarity of the time series sounds like a complex statistical matter, but one can simplify it and just think about it here now for this model as implying that the mean and variance of the outcome are time invariant. That sounds a little bit restrictive, but it's not really a modeling limitation, but a necessity so that the model matches the data that we're considering. I'll tell you what I mean by that. So without variance stationarity, data would have values that explode over time due to increasingly large variances. So it's data with exponential growth. That is not data that we typically see in our applications. And we will take a look at that, take an example of that. Now just look at this bullet here. If you consider this AR1 model, that is lag1 autoregressive model on the within level, dropping the W superscript and just writing it like in 15 here. Stationarity for the variance, assuming residual variance is theta, which is the same across time. Stationarity implies that the absolute value of this regression coefficient needs to be less than 1. So an autoregression, autocorrelation slope less than 1. Now, what if that is not the case? On slide 50, I take a look at stationarity versus non-stationarity more explicitly. So we consider this expression on the within level, PA at time point t related to PA at time point t minus 1, with autoregressive coefficient beta and the residual epsilon. Now, we can ask, what is the variance of that expression? Well, it's the variance of the first part plus the variance of the second because they're uncorrelated. But what is the variance of the first part? What's the variance of PA at t minus 1? Well, here, that's not easy to say. But here we can use the stationarity, which implies that the variance at t minus 1 is the same as the variance at t. So the variance of PA at t is the same as the variance of PA at t minus 1. We take the variance of that part. And that makes it possible to solve for this variance. You move this term over to the left and divide by 1 minus beta squared, and here you come out with this expression. Theta is the variance of epsilon. And if beta is absolute less than 1, then that will be a positive variance. And there you have it. That's a variance on the within level that we don't print in the Mplus output. We only print beta and theta, but we don't print the total within variance. But through model constraint, you can express this if you're interested in it. And we're going to show how we do that to compute the intraclass correlation. Now, the variance stationarity also implies that these unstandardized beta coefficient, regression coefficients, are the same as the standardized. Because the standardization means that you divide by the dependent variable standard deviation and multiply by the independent variable standard deviation, and since they are the same, they cancel out. So that clarifies things. Now let's take a look at the opposite situation, non-stationarity of variance. So let's consider 10 consecutive time points, and let's say that first time point has variance 1. We're going to see how the variance develops over time when we don't have stationarity. So the variance at the second time point then is the expression, the second time point is by this formula here, is beta times PA 1 time point earlier plus epsilon at that time point 2. And that will be the square of this beta times the variance of time 1, which is 1, plus residual term, which we assume are going to be small enough here not to stack up against the beta term. Same thing for the third time point. Then we take the expression here, variance of that, which is a PA at time point 2, time where we multiply that by beta and add a residual for time point 3, and then we get beta squared, and the variance of beta squared is beta to the power of 4, where the rest will be even smaller relative to this term, etc. So then, going to the variance of the 10th time point is totally dominated by the first term, this term, beta 2, beta 4, and here it is beta 2 times 9. So beta to the power of 18. So for instance, if we have a beta of 1.5 that is not within the stationarity range, that would result in the variance at the 10th time point being 1.5 times 18, which is 1,478. So a very large variance, and you can then imagine that if you generate data with such a model, the values would explode over time. Now we can also consider non-stationarity of the mean, which may occur with a trend over time. But then we could model that. We can use as a function of time as a covariate, so that residual DSEM, which we will talk about soon, can be applied with stationarity for the residuals, for what's left after we have accounted for a function of time used as a covariate. So let's take a look then at slide 51, where we look at the input for this model 1. I want to add that the outputs for the key runs here are posted on the Webtalk site. So here we have then, we start with use variables. This is within the variable command, so up here you have the variable colon command name. And we select people that don't have more hours than they should in the data, and we get rid of some people that don't change in terms of PA over time. And then we include this lagged option, which triggers time series analysis, DSEM. And here we have lagged with lag 1, so we could add, could say 2 here instead to have a lag 2 model. And then a new feature in version 8.9 that I will talk about on the next slide is that T-interval is handled differently now for two-level analysis. And I'll specify that explicitly on the next slide. So here we take then the hours variable in the data and say that we want to use T-interval equals 2. And the new variable that is going to be used for the analysis is called time. So the user gives that variable name and can choose any variable name there, but hours is the time variable named in the data. So this two-level analysis using base and a minimum of 1000 B iterations is used here, and then the model is PA on PA ampersand 1, and we're going to label that R for reasons that will become clear. So that's the autoregressive coefficient, and PA is the residual variance in that relationship on within. And then we label the variance on between as well, because what we're going to go after here now is make the connection with intraclass correlation that we talked about in the regular two-level analysis. So we're going to compute two new parameters, the within variance and the ICC. So within variance is the total within variance, which is time invariant under stationarity, and that is equal to the square of the correlation order regression. This is what we call beta before, times the same thing, that doesn't change from the 2 time points, plus the residual variance, which means that this is equal to residual variance, what we call theta before, divided by 1 minus the square of the autoregressive coefficient, which we call beta before. So that's the total within variation. And then the ICC is the between variation, which we got here, up there, divided by between plus within, which is the total variance here. And out comes an ICC of 0.56. I'm not giving you, so we just summarized that fact here. And also in passing, once again, I want to emphasize that you want to use Tech 8 to look at the convergence, to gauge whether or not you need more B iterations to be sure that the PSR convergence criterion is staying close to 1 and not starting to drift up again. And we want to always use type equals plot 3 with base, because there are a lot of base related plots that we want to take a look at. And I'm going to show you that in a second. Now, regarding T-interval, there has been changes in version 8.9. We've changed it so that it works the same way for two-level and cross-classified DSEM. So two-level has changed to the cross-classified style, which means that the initial missing values for an individual, if you go back to my T-interval discussion, you'll see what I mean, are no longer dropped for two-level, but are included. And that causes changes that are very, very small in the estimates. So you can ignore differences compared to past runs that you have done. But if you insist, you can get the old approach by adding the setting drop as a third argument in parentheses for T-interval. And also the original time variable, which is called hours in this example, is no longer changed by T-interval. We don't want T-interval to change your data that way for the analysis. But a new time variable that the user names is used in the analysis. That's time in the example. And that variable can be modified and defined if you want to. You can have functions of time, for instance, as a covariate. And if no new time variable is used and named by the user, then this underscore b int is used. Bin is what b refers to. Bin is the word that we used in the T-interval discussion earlier on. So here then finally we have the output excerpts for model 1 in this DSEM step 3. You have the within level results and the between level results. And on the within level you have the autoregressive coefficient here, 0.4. And you have the standard deviation of the posterior distribution, which, as I say here, corresponds to conceptually corresponds to the standard error for maximum likelihood. So therefore, the estimate divided by the standard deviation is approximately a normal z-score. So you can think of it that way. But the confidence interval is a better statistic to report. That is, you should report this: lower at 95%, lower 2.5% and upper 2.5%. So 95% interval, and it doesn't cover 0, which means that the coefficient is significant. So we give it an asterisk there. Now for residual variances here, or variances here. You can look at the variance here on between level. With base, variances are always significant, in the sense that the confidence interval, or credibility interval as the Bayesians call it, never covers 0. The Markov chain Monte Carlo algorithm keeps it positive. So what we do, Tiemer suggests gauging the importance of a variance by looking at the ratio of the estimate to the standard deviation, which is then an approximate z-score, and he argues for having it be at least 3 to be a substantial variance to care about. Otherwise, one would specify it as fixed, not something varying. And here, of course, this ratio is approximately 10, so there you have a clearly important variance that you need to include in the model. Same for the residual variance here. You also get the standardized results here, STD/YX standardization on the within level and on the between level. So you see here that on the within level, the regression coefficient is the same, standardized and unstandardized, and that's because of the stationarity. It wouldn't be so otherwise. And the residual variance on within standardized is 0.828, so the within level R² is 1 minus 0.828, so 0.172, which means that we have a lot of room to improve the prediction of positive affect by perhaps other variables, other predictors in the model. Now, slide 55 then, we can take a look at the summary of the results for this univariate analysis, DSEM analysis of positive affect, comparing the different time interval choices that we discussed in an earlier segment. So we have time interval 1, 2, and 3. And we can start with the time interval plot information. I'm going to show you a plot of this later on. And we talk about SMSE, which is a metric is hours, so it's a distance between the actual time and the time that we use in the analysis. And the average then, that average difference is very low, which is good, with t interval equals 1. It gets a little bit worse for 2, and more worse still for t interval equals 3. So this says that you're on average you have almost 2 hours time difference between actual time and time used in analysis. Whether that's seriously important in applications or not is depends on the substance of the analysis. You can also look at the maximum discrepancy for any one person at any one time point, and the maximum is 4.5 here. I think we print an error message if it's over some much larger value than that. I can't remember which value. Now the missing data coverage then is quite low for time interval 1. That is, we add a lot of missing data with t interval 1. A lot of missing data rows in the data. The coverage goes up for 2 and further up for t interval equals 3. This is not to say that these are problematic values. It's just that with this low coverage, you can have problems with more complex models. So I'm saying here t interval equals 1 matches the data best, but the low coverage, that is the many missing data rows, can make convergence difficult for complex models, particularly random effects models. And then you can also take a look at the within estimates, the autoregressive coefficient, which is higher for close measurements than it is for measurements further apart. So it's natural that it goes down with larger distances here. However, we note that they don't go down according to the theory of lag 1, because 0.414 is not the square of 0.547 as expected. So that's just suggests that maybe lag 2 is needed in the model. As the autoregressive coefficient goes down, the residual variance naturally goes up to keep the total variance the same, stationary, as we talked about. The between level means don't change much, nor do their standard errors. Between level variance don't change much either. And we're going to come back to this kind of comparison of the different time interval choices, how they relate to the parameters in the model a little bit further on in this web talk, and see how much of a change you have in a model that is richer than this univariate model.